Good evening and happy Monday. Last full week. So today we're going to finish up applications of the derivative, right? We're going to look at intervals of increasing, decreasing, as well as intervals of concavity, convexity. Included in this is looking at first derivative test, second derivative test, which I won't be using in this problem set, for determining relative extrema, right? Whether a critical point is a min or a max. We also look at points of inflection. All right, we finish this evening up by looking at optimization problems. But so we already discussed last time what we meant by a critical point. All right, so we're going to be looking at a function with domain D. I want sum over. All right, so function f is said to be increasing over some interval that is a subset of the domain. If f of x1 is less than or equal to f of x2 for all x1 less than x2 within the interval. I should probably say whenever. Yeah, I'm going to reword that. For all x1, x2 in the interval such that x1 is less than x2. Right, so as you move right, from left to right, your function values are getting larger, right? Or they stay the same. I mean, now technically speaking, it should just be greater than, right? F of x1 greater than f of x2. Right? If they're equal, then it's considered to be constant. However, even if it goes constant for a little bit, we still say it's monotonic increasing. All right, amount of time decreasing or just decreasing. Right, same thing, except as you go from left to right in the interval, right, your function values are getting smaller. Right, with, again, you can have some periods of constant. Right, function is said to be concave or concave up over an interval that is a subset of the domain if f prime of x is increasing on that interval. Right, and the function is said to be convex or concave down over an interval I subset of the domain if f prime of x is decreasing on I. All right, so these are definitions of the intervals. All right, there's one more definition. right? X equals I is an inflection point if your function switches concavity at that point, right? So it goes from concave to convex or from convex to concave at that point. Now for the tests. Yeah, I'm ready now. Function f of x is increasing on the interval I if and only if its derivative is positive over that entire interval. Right? F of x is decreasing on the interval I if and only if its derivative is negative over the entire interval. First derivative test. I don't think I want to word it that way. I think it's this way. If f prime of x changes from positive to negative, that's how I word it. So if f prime changes sign from positive to negative at c, then f of c is a relative maximum. Right? In other words, if f of x switches from increasing to decreasing at c, f of c is a relative max. If f prime of x changes from negative to positive at the point then, so at the point x equals c, right then, f of c is a relative minimum. Right? So again, if f of x is switching from decreasing to increasing at c, then f of c is a relative minimum. Test for concave convex. That's why I word this, yes. Function f of x is concave on an interval I if its second derivative is positive over the entire interval. And then a function f is convex on an interval I if f double prime of x, second derivative is less than 0 everywhere on the interval. Second derivative test. Let C be some point in the domain of F such that F prime, I'm sorry, it should be F prime of C is equal to 0. If f double prime of c is greater than 0, f of c is a relative min. If f double prime of c is less than 0, f of c is a relative max. If it equals 0, so f double prime of c is equal to 0, the test is inconclusive. Right? This means it could be either a min, a max, or neither. All right, so this is the second derivative test. And there is a corollary to this. No, let's do this. This is the only critical point. If it happens to be the only critical point in an interval, then the second derivative test gives an absolute extremum, not just a relative. So the second derivative test, along with its corollary, will be used in optimization problems. And so what we're going to do for all these problems is find the intervals where it's increasing and decreasing. We'll list out all the relative extrema. Find the intervals where it is concave or convex, right? Concave up or concave down. And list out all the points of inflection. First thing we need, f prime. Two x minus 2, right? We want to find critical points. Remember, those are points where f prime is 0 or undefined. Well, 2x minus 2 is linear. It's defined everywhere. So we're just going to set it equal to 0. If you factor out a 2 and divide, this would mean that x minus 1 is 0. So we have a single critical point, c equals 1. All right, so real quick. So let's say we're going to have some function, right? In this case, it's starting off negative. Doesn't really matter, right? To go to positive, there are two ways that can happen. Right? There's either a break in the function, right? So this is one example of a break. Another example of a break could be something like that. Right, so this would be a case where the derivative is undefined. The only other way the function goes negative to positive would be crossing across the x-axis, right? Let's just say it does something like that. I don't care. Right, and that point is where the function would equal 0. right? So here the derivative is 0 at the point 1. This means that everywhere except at 1, the derivative will be either positive or negative. So once we have critical points, we now list off our test intervals. And to determine test intervals, you just take the domain of the original function and split it at your critical points. Domain of f is all real numbers. Interval starts at negative infinity. We'll split off at 1. Right, and then it's going to continue to positive infinity. Now you just have to determine the sign of f prime in each interval. To do this, we take a test point from each interval. All right, so let's just say here, take the test point 0. Plug it into f prime. And use that to determine the sign. Well, f prime of 0 is negative. I don't care what the actual value is, right? We're only concerned with its sign. Do the same thing here. Pick a test point, plug it into f prime to determine its sign. 2. F prime of 2 gives you positive. Function is increasing whenever the derivative is positive. Function is decreasing whenever the derivative is negative. Go back to the table. Look for whenever the derivative changes sign. Minus the plus, it changes sign. So it switches from negative to positive at 1. So the first derivative test tells us f of 1 is a relative min. Right, so go back up to f, evaluate f of 1. Looks like 0. Now we want the second derivative. It's just 2, isn't it? Two is clearly defined everywhere. And 2 will never equal 0. This gives us no critical points. So once we've done that, we play the same game as we did, right? Because remember, concavity convexity is determined by the increasing or decreasing of f prime. So we're just doing the exact same thing we did, except we're testing f double prime instead of f prime. We take the domain of f and split it at any critical points we get, which there are none. Pick any test point, plug it back into f double prime to find its sign. Wherever the second derivative is positive, it's concave. Wherever the second derivative is negative, it's convex. So it's concave everywhere and convex nowhere. Inflection points are anywhere that the concavity switches. So you just go back to the table and you see if it switches sign and where. Well, it's never switching sign. So there are no inflection points. Oh, lovely. First, find the derivative. Determine where that is undefined. It's undefined at nowhere. So now set it equal to 0 and solve. Factors of 2 and 3 and added give you 2. There are none. So we have to use quadratic. Negative b plus or minus the square root b squared minus 4ac, 4 times 8 times 3, all over 2a. All right, this can't happen. So we get a negative under the square root. So there are no critical points. Means we only have a single test interval, and that's the domain. Zero's in there. Throw it into f prime, you're going to get a positive value. Right, so we're increasing everywhere, decreasing nowhere. Which means there's no extrema. Now we want f double prime. That is defined everywhere. Set it equal to 0 and solve. Means our critical point's 1/2. take the domain of f, split it at those critical points, right? So those would then be your test intervals. This first interval contains 0, throw it into f double prime. Get negative 1, throw it into f double prime. You get positive. Positive means concave. Negative means convex. Wherever it switches sign, we have an inflection point. Switches sign at a half. So plug a half back into f. I got 9. First derivative. It's defined everywhere set it equal to 0. Factor out a negative 12. All right, that negative 12, we can divide it out. We can now do factor by grouping. All right, so group the first two terms together, factor out an x squared. Group the second two terms together, factor out a -1. That leaves us with x minus 2 times x squared minus 1 is equal to 0. That gives us 3 critical points: -1, +1, and +2. So take the domain of f and split it at the critical points. So we start at -infinity, goes up to the first critical point, -1. Then continue at -1, it goes up to the second critical point of 1. Continues until the third critical point of 2, right? And then it'll just continue on forever. Four test intervals. Take any value, plug it back into f prime. Now, here's an easy way of doing it. Let's just pick -5. Why not? If you plug -5 in here, you get negative, right? Here you'll get positive. So negative value times positive value is negative. But remember, we divided out by a -12. So this value is positive. This contains 0, so I play the same game. Negative times negative is positive, but we divided out a negative. So it's negative. One to 2, 3/2. Negative, positive, but we divided out by a negative. So we get positive. And then any value in here, 5, right? Positive times positive, but we divided out a negative. Perfect. Lovely. Okay. So I'm currently getting a storm. And of course, whenever there's a storm, there's a chance of losing power. So there's a chance of me being disconnected. Fair warning. Everywhere you see a positive, right? All the positive intervals means the function is increasing. Negative intervals means the function is decreasing. Positive to negative means we have a max. At -1, go back up, plug -1 back in. I got 21. But we switch positive to negative again. So we have another relative max at 2, right? And again, we want f of 2. I got -6. Switches negative to positive. Which means there's a relative min. Right? Switched at 1. So plug 1 in to F. I got -11. Now we want f double prime. Negative 36 x squared plus 48x plus 12. All right, so that is defined everywhere. Let's factor out a negative 12. Divide out negative 12. Now, can 3x squared minus 4x minus 1 be factored? No, it cannot. All right, so we have to use quadratic formula again. I'm too lazy. Oops. Let me. Update the password. Go back to sharing my screen. Uh, 150, I think we used. So I need my keyboard. All right. So we can just use a CAS to solve equations for us at this point, right? This is not an algebra class. So the command is solve. Capital S. Right now we just type in the equation. Well, that's an up. Oops. And so 3x squared minus 4x minus 1 equals 0. So notice I'm using a double equals here. Right, so single equals, you're storing a value. Double equals is a test. And I need to tell I'm solving for what variable, in this case x, close out my bracket, shift, enter. Okay, now there are the two solutions. I personally do not like that form. I think it's this. So I'm just going to do table form. Oops, not FOEM. There we go. Just so it lists it out more nicely for me. There's our two solutions. Let me try 175 per. Oh, no, 200's the next. That'll work. So there's the two critical points for f prime, or of f prime. So we're going to have three test intervals. Negative 10 should be in this interval, right? That's a safe bet. Going to plug it in here. Yeah, clearly going to be positive. But then multiply by the negative 12, you're going to get negative. Zero is in this interval. Plug it in, you're going to get positive. And I can choose 10 here. And it looks like it's negative again. Remember, concave, wherever we're positive. Convex, wherever we're negative. And then wherever that sign changes, we have an inflection point. Sign changes twice, so we're going to have two inflection points. One there. All right, we need to plug it back into F. What was F? There it is. I got 80 root 7 minus 13 all over 27. Which means I need to go back up to the function. Of course I do. This time I got negative 80 root 7 plus 13 all over 27. Why is it forbidden? Who knows? That's odd. Why it won't let me see the warnings? There we go. Okay, so severe thunderstorm warning until 8:30. Lovely. So now we're going to look at secant of x on this interval. We should have time for this. So notice that this is now a function that does not have domain of all real numbers. So I'm going to list out the domain. Right, so secant of x is undefined at every odd multiple of pi over 2. So on the chosen interval, this is our domain. Derivative of secant is secant tangent. So both secant and tangent have the same domain. So this is defined everywhere on our domain. We just set it equal to 0 and solve. We get either secant is 0 or tangent is 0. But secant cannot be 0. So that leaves with tangent being 0. Tangent is 0. At every multiple of pi. However, we're only interested in those values in our interval. So we have negative pi over 4. No, I'm sorry. There was one before that, right? There is negative 5 pi over 4. Then we get, what am I doing over 4 for? Oh dear. I'm looking at multiples of pi. Okay. Negative pi, 0, and positive pi. Quite a few test intervals. However, an understanding of the trig functions makes this simple. All right, positive increasing, negative decreasing. All right, where are we changing signs? Where we go plus to minus, it's a relative max. And secant of negative pi is -1. We go plus to minus again at pi, and that's also -1. We go minus to plus at 0. Secant of 0 is 1. So there's the relative max and relative min. F double prime. We need to use product rule. That's defined everywhere. That statement is a contradiction. That will never be 0, so there's no critical points. Right, and understanding of the trig functions again makes this a simple matter. Concave wherever it's positive, convex wherever it is negative. We have 2 inflection points. One at negative pi over 2, and secant of negative pi. I'm sorry. Yes, it is changing sign at negative pi over 2 and positive pi over 2. But they're not critical points. They're not in the domain. So there's no inflection points. Any questions? So then why don't we do this? We'll take our break. Started 5 minutes late. So let's say break will run till 7:55. Come back and we'll look at optimization problems. All right, and we're back. We're looking at optimization problems now. All right, so in an optimization problem, we're going to be given a specific quantity that we want to optimize. So either maximize it or minimize it. So much like related rates, the toughest part of these problems is coming up with the equation. So we're just going to jump right in. And it looks like I got lazy. Oh my. No, that's still pretty good, actually. So the first thing we want to do, just like with related rates, is draw a picture. Well, in this case, picture's not going to help, right? So ignore the picture here. But we still want to label unknowns, right? Maximum product of two numbers. Let X and Y represent the two numbers. We're looking to maximize the quantity X times Y. Under the constraint that their sum is 100. Well, if the sum is 100, that would mean that Y would have to be 100 minus X, right? So we can now write the quantity that we wish to maximize as a function of a single variable. It's called P of X. So here's the function that we wish to maximize. We also need a reasonable domain. Well, in this case, domain for X would be all real numbers. Take the derivative. This means C is equal to 50. That is our critical point. Notice it's the only critical point in the domain. Second derivative test is going to give us an absolute extremum. Take the second derivative. Evaluate it at our critical point, and we're going to get less than 0. This means that 50 results in an absolute max. So when X is 50, we've maximized the product. If X is 50, Y would also have to be 50. So the two numbers that maximize the product, whose sum is 100, is 50 and 50. We wanted the maximum product. So the maximum product is 2,500. Find the minimum sum of two positive numbers whose product is 500. And so again, draw a picture, label quantities. Oh, there's no picture. So let's just label some quantities. So we say let X and Y represent the two numbers. Looking to minimize X+ Y . This time we have two constraints. Both x and y have to be positive, and x times y has to be 500. Well, if x times y is 500, y would have to be 500 over x. Sum. I don't even know why I did that. I don't want that. X plus 500 over x, there's the function that we're looking to minimize. We need its domain. Positive reals. 0 to infinity. Take its derivative. Defined everywhere over our domain. Set it equal to 0. X squared minus 500 would be 0. I'm going to do it this way. So we're going to get either negative 10 root 5 or 10 root 5. Right. However, our domain, positive real numbers. So only one of these is a critical point, and that's positive 10 root 5. Take the second derivative. Evaluate it at our critical point. We're going to get a positive value. Since we have one critical value in the interval, this is an absolute extremum. Right, so this results in a min. This really, I'm trying to keep it consistent. So let's move it up. X is 10 root 5. What does that make Y? Well, it's be 500 over 10 root 5, 50 over root 5. Which is also 10 root 5. So the minimum sum is 20 root 5. It's annoying that doesn't let me cop or crop. I mean, the only thing I can do is do this. Good enough. Find maximal area of a right triangle with hypotenuse of length 1. So there's our picture, right? We have the base, which is A. We have the height, which is B. Hypotenuse is 1. We're looking to maximize 1/2 A times B. Right, that's the area of this triangle. Notice that we do have a constraint. We have to have a squared plus b squared equal to 1. Solve for either A or B, doesn't matter. Right, so B is going to have to be the square root of 1 minus A squared. So we get the area as a function of A, 1/2 A times the square root of 1 minus A squared. We need a feasible domain for A. Well, we know that A has to be positive. And A can't be 1 or larger. A prime. Well, we're feeling kind of lazy. Of course, it's going to make me sign back in. One half times A times square root of 1 minus A squared. I'm going to go ahead and define a function. And I'm going to go A prime of A. don't like that. So simplify percent. There we go. Right, so the percent simply is the last output. So this is just saying simplify that last output. Right, so that's defined everywhere in our domain. Set it equal to 0. We're going to have either plus or minus 1 over root 2. But since A has to be positive, critical point is 1 over root 2. Now find A double prime. All right, so this I'm just going to go right to the simplify. Simplify A double prime. Right, there's our second derivative. We want A double prime of 1 over root 2. And we get negative. That means that this is resulting in a max. This means both A and B are 1 over root 2. All right, so the maximum area is a quarter. Oh, sure. Okay. What is going on? Okay. Oh, there you are. Okay. Yep. Ranch has 1,000 feet of fencing in which to construct adjacent, equally sized rectangular pens. What dimensions should these pens have? to maximize the enclosed area. That looks good. It's too crooked. That looks close enough. Let's call that Y. Call that entire thing X. We are looking to maximize the area of each pen. Since they're equal size, we just need to worry about one of them. X over 2 times Y. With a constraint that we only have 1,000 feet of fencing. So that's going to be what? Two X plus 3Y has to be 1,000, right? That means that Y would be thousand minus 2X all over 3. For 500, oops, should be 500X. All over 3. Feasible domain. Right, well, again, X is measuring a length, right? So it has to be positive. And what is the maximum it can go up to? If y is 0, then x would have to be 500. Right? So how I got this, right, is if y was 0, what would x have to be? It have to be 500, right? But y is not going to be 0. It's going to approach 0. Excuse me. It can approach 0, right? Excuse me. But will never actually hit 0. So x is approaching 500 in that case. Right, so let's take the derivative. Be 500 minus 2x all over 3, right? Defined everywhere, so set it equal to 0. 500 minus 2x has to be 0, which means x would have to be 250. So that is our critical point. Let's take the second derivative. It's what? Negative 2/3. That's the second derivative evaluated at 250 is less than 0. So this results in a max. So we get x is 250 feet. And what is y? Be 500 over 3, right? We're looking for dimensions here, not the area. So the dimension should be 250 feet by 500 over 3 feet. Right? Those dimensions result in the maximal area of the two pens. United States Postal Service charges more for boxes whose combined length and girth exceeds 108 inches. So what is the maximum volume of a package with a square cross-section that does not exceed the 108-inch standard? All right, so let's draw a picture first. All right, so square cross section. Actually, I'm not going to worry about it just yet. Let me finish drawing. So let's say there is our rectangular box. We'll call this Y, call this X. Square cross section means this is also X. We're looking to maximize volume of this rectangular box. Volume of a box. Length times width times height, right? So it'd be Y times X squared. And we don't want it to exceed the 108-inch standard, right? So that's length and girth. Well, length in this case is Y. The girth is perimeter around. Which is 4x. Right, so that's the equal 108. This, of course, means that Y would be the 108 minus 4x. And so we can write volume now strictly as a function of x. (108x squared minus 4x cubed). We need a domain. It's going to be 0 to 108 over 4, which is 27. Let's go ahead and take its derivative. Factor out a 12x. What are we left with? (18 minus x). Right, we're going to get x is 0 or x is 18. But our domain is 0 to 27. It's going to be open, right? So it gives us a critical point of 18. Take the second derivative. Determine that sign. That sign is negative. This results in a max. X is 18, which means Y is 36. And we wanted to what? Find maximum volume. (11,664) cubic inches. Are there any questions? Okay. So you have two assignments, two math assignments that will be due on Wednesday. The report on shape of a graph, extrema, increasing, decreasing, and concavity. Let me double check. I think I have that set to be due tomorrow, 11:59. Right, and then your third unit test is due before the start of class on Wednesday. On Wednesday, we will start integration. So we start it by considering the area problem. So given a graph, a positive graph, we want to find the area between that curve and the x-axis. That's the area problem. And that works right into the integral because that area is the integral. And we're going to see that the integral is just a limit. Right? Just like the derivative was a limit, which means we spent the entire semester studying one thing, the limit. Also on Wednesday, we will look at the antiderivative, right? So this is all building up to Thursday, which is the fundamental theorem of calculus. And the fundamental theorem of calculus relates derivatives, antiderivatives, and integrals. Right? This is like the crux of Calc 1. All of Calc 1 leads up to this theorem, the fundamental theorem. Right now, keep in mind, we're just doing a basic introduction of integration. We're not going to delve too much into it. We're not going to look at the applications of it this semester or this term, right? That's in Calc 2. All we really do with the integral and antiderivatives is just do some basic antiderivatives, and we look at one technique called change of variable, or U-sub. Again, Calculus 2 is when you'll study more of the techniques of finding antiderivatives. In general, antiderivatives are a lot tougher than derivatives. Right? And we'll not only see that when we study the definition of the integral on Wednesday, but if you move on to Calc 2, you will also see how much more difficult integrals and antiderivatives are than derivatives. That's going to be it for me for this evening. Have a wonderful rest of your night. See you again Wednesday at 6 p.m.
Thank you.